Hello again, everyone. All right, so let's continue going with our discussions about language modeling approach to information retrieval. Let's start off with a small example problem. All right, so let's say we have document 1 here, and this document says Bob was bit by a shark while swimming at the beach. Poor Bob. By the way, there are 11 words in this sentence, and let's say we're using our standard sort of way to tokenize and turn it into words. Pretty simple. Document 2, Mars attacks really jumps the shark. This is sort of more of a nonsense sentence, but it's got some words in it, which is good. And this has 6 words in it. All right, so we're going to query. This is our collection. All right, pretty small collection. Our query, we're interested in shark attacks. Okay, and what do we need to do? We want our problem being posed to you is to compute the query likelihood for docs 1 and 2. All right, so got this query, and we want to compute the likelihood of this query given document 1, and then the likelihood of this query given document 2. Shouldn't be a problem. You really should try, actually, on your own to do this, but I'll continue right now and show you how to do it. All right. So let's make myself a little more space by doing a lot of erasing. All right. So we'll remember that we've got these 2 words, shark attacks, and then the first sentence, Bob was struck by a shark while swimming at the beach. Okay, so to do document likelihood for document 1, I mean, not document likelihood, query likelihood. So the document 1, so shark, how many times does it appear in the first sentence? Bob was bit by a shark while swimming at the beach. It occurs once. There's 11 words. So the probability of, I don't know, I write this out. So this is, let's do the probability of a query given the document. And so we're going to have, this is the probability of shark given doc 1 multiplied by the probability of attacks given doc 1, right? And so this will go ahead. So there's a shark appears once out of 11 words, and we'll multiply this by oh, poor doc 1 doesn't have the word attacks in it. It's a 0 out of 11. And so the likelihood of the query coming from this document is 0. All right. And the probability of our query given the second document, again, probability of the shark given document 2 multiplied by the probability of attacks given by document 2. And I'm actually doing a little bit of a shorthand here. I'm really saying, let's do, I've got this model of document 2, this model of document 1, and my model of these documents is a maximum likelihood estimated model to come up with the probabilities for those documents. Anyways, so this guy happens to be shark. So again, really jumps the shark, occurs once, and a tax occurs once. So the probability is 1 over 36. All right, so then I could rank my documents, and this document would come first, and this document would come second. You, of course, know, by the way, that the first document is a lot better probably for shark attacks than the second one. And I think the most frustrating thing, though, is think about this in a big collection. Documents like document 1, which they do talk about sharks, okay, but they fail to mention the word attacks, are going to always get a query likelihood score for them of 0 for if they're missing one of the words. And that's really unfortunate, because essentially when we have documents of scores of 0 in our retrieval setup, we do not return them. Okay, or they'll be placed way at the bottom of the ranking and we'll never see them. So even if a document, let's say, contained sharks a lot, nope, missing the one word attacks, you're gone. You're completely thrown out. You have 0 probability anymore, truthfully, of have produced that query, because you didn't have that word. And we estimated your probability of producing that word attacks as 0, that word that's missing from your document, because it wasn't there. So why should we say there's any probability of it occurring? Well, so this is quite sad. All of a sudden, you should go, wait a minute, Mark. You're basically going to tell me now this whole language modeling approach to information retrieval ends up being a fancy version of a Boolean and, a conjunctive query. In other words, I must have all of the words or my score completely goes to 0. That doesn't seem like a good retrieval method. You were telling us that this is a okay retrieval method, and it's actually quite good. And the issue is, yes, we have what is known here as the 0 probability problem. Okay, so 0 probability problem. Or you want to talk about how to get rid of and how to deal with these 0 probabilities. Because this document has one of the words in it. It shouldn't get completely given a score of 0. And in fact, if you were to do retrieval with this setup, you would get very bad results, just as we've seen with Boolean and. It probably would be better than Boolean and, because at least for the documents that do have all of the words, they'll be ranked, all right, in some fashion. So it would at least induce a ranking on those. But there's still going to be all these documents that by missing one word are completely excluded. And this is especially sad if we keep making our queries longer and longer, which should be better and better. A user tells us more and more about what they want. We should do better. But it's more likely that we'll just throw out documents because they're missing a word. So we've got to solve this. We've got to solve this 0 probability problem. And the answer to this is smoothing. Okay, just so you know, what the word I'm saying is the answer is smoothing. I like this word because it kind of makes sense for when we'll see what it does. I also like it because it's it's almost like a nonsense word. So it's not an issue to learn the vocabulary. I always hate it when there is vocabulary to learn and it absolutely conflicts with my existing concepts of what the word means. Anyways, let's go to a simpler setting away from talking about documents and words with all of their, especially these documents and the collections with these huge vocabularies and all this stuff. Let's really simplify. So let's talk about a six-sided die again. Okay, so we'll talk about a six-sided die. All right, so a six-sided die, you know, for those of you who maybe have, you've all seen a six-sided die. You know, it's a nice cube, and it's got these little pips on them. And in fact, I actually don't memorize where the pips are, so I really don't know if I was to be doing this correctly. Anyways, so on each side we see the number of dots or pips or whatever they are to tell us. We could even, I guess we could write numbers 1, 2, 3, 4, 5, 6 on them. Anyways, so we've got this die. In the world of examples that we love to use for mathematics, we don't just have fair die, but there's biased die. So there's a whole range of dies in the world. And each one, just like documents, you know, are going to have different probabilities for the vocabulary, for the numbers. You know, so we've got vocabularies for words, and we're going to have all sorts. Each document's going to have these different probabilities for these words. And let's envision we've got this universe of die out there, and they're going to have different probabilities. We're going to need to model a die. All right. Now, so I want to ask you this question. So you have a die in hand. So I don't have an example die. If I did, I'd have it in my hand right now, and I would show it to you. There. All right. So you have a die in hand, and you want to estimate the probability of, you know, you're going to roll it given that die. So this roll could be probability of a 1, probability of a 2, probability of 3. You want to figure out the parameters of this model, the model of the die, and you have one in your hands right now. And I'm going to tell you, in fact, that let's pretend that you actually have a biased die. I know it's a biased die, and it's in your hands right now. And so in other words, by biased, it means that the probability of 1 is not equal to the probability of 2, is not equal to the probability of 3, and so on. And you have it. It's there in your hand. And your job is to estimate this. What is your feeling about what you want to do? I know what I want to do. I want to roll the die. I want to roll that die and see what it does. I want to actually poke it and test it and find out, really, what is the probability of a 1? What is the probability of a 2? I want to roll and roll and roll and roll. I want to take samples of this actual thing, and I want to find out what is the probability of 1, what is the probability of 2, and that would be my best model. Okay? Basically, I would produce this really, I want to sample it over and over, and I get all these rolls, and then I would apply maximum likelihood estimation based upon that data that was collected, and I would use those as my estimates of whatever the true probabilities are. I don't know what, I'll never know the true probabilities. I could only sample it and find, you know, and estimate what these probabilities are. Only in mathematical problems would we know the true probabilities of something. In the real world here, with this die, I'm not going to know its real probabilities. I'm going to only be able to estimate it by taking samples, by rolling it, and then based upon those samples, I could take the maximum likelihood estimate, and that could be a good estimate as to what the actual probabilities are. That would be my nice model of my die. The actual die is that physical die rolling on some surface in a certain atmosphere and temperature and humidity and so forth and so on. All the randomness of the world at hand. But my mathematical model would be a nice multinomial model, and I would have estimated the probabilities. All right, you get the idea. Now, I'm going to say to you this. Before you've rolled the die, now if you knew nothing else, and in fact, let's say I hadn't told you it was a biased die, all right, if you knew nothing else, what would you estimate the probability of a roll given the die to be? Yeah, I'm pausing. All right, so this is a good question, I think. You know, I could tell you it's biased, but you don't know. I'm not telling you in any which way it's biased. And I want you, though, to come up with your best guess of how to assign probabilities to this guy. And you're not allowed to roll it yet, okay? So you're not allowed to do what, oh, you really want to do. You really want to roll it. You cannot actually roll it yet. Well, there's two kind of ways to think about this. One way is to just basically go ahead and say to yourself, you know, I don't know any better, all right? Without any other knowledge, my best guess would be to give it uniform, what we would call prior probabilities. All right, and so let's think about that. Let me draw it as this picture here. I like this picture. 1, 2, 3, 4, 5, and 6. These are little bins, or I can keep track of counts. So if I was to be rolling it, and I rolled a 1, I would put a little X here. If I rolled a 3, I'd put an X here. If I roll a 1 again, I put a little X here. And I could keep track of my rolls, and at the end I would look at what was in the bins, okay? And then I would be able to do my maximum likelihood estimate after I'd done this 100,000 times or something like that, all right? But I'm not allowed to roll it. So, and I say to myself, I think there are, I'm just going to say, since I know nothing else about this die, let's assume it has a uniform probability of coming up with any of these. So it's like me putting a little, as though I had put in a roll for each of these here. All right, so now with this, I can go and I can say, all right, I haven't rolled it, but I'm going to pretend like I kind of did. And I can then calculate the probability, the maximum likelihood estimate. So this will be 1 over 6 rolls. And so I got uniform probability here. Pretty nice, okay? What we do here is we call this, when we do this, and we stick in these, we call these pseudo counts. So this notion is to add 6. I always find pseudo a hard word to spell. Pseudo counts. we're going to put one count for each value. And then, as I said, now our maximum likelihood estimate says there's a uniform probability for each of those, 1/6. All right. Now, so this, I'm going to stay on this uniform prior probabilities for a little bit. Now, what's interesting about this is I can go ahead and I start here. So this is what I could go with when I know nothing about the die. These are my pseudo counts I've gone ahead and added. But then what I can go ahead and do, so I now have my first model of the die. I have these probabilities. So my model is, and I estimate, based upon knowing nothing else, that it's 1/6, 1/6 for probability of 1, 2, 3, 4, 5, 6. And so I could use that model, but we know it's probably not a very good one. And so yes, we really should go and roll that die sum. And so what the thing is, now to get a better estimate, we can roll the die, as I said, to sample it. Okay, so I roll the die and it comes up 2. I've taken one sample of it. I still am able, if I wanted to, I could stop right there and I could calculate the probabilities for my model. So 1/7, 2/7, 1/7, and so forth. And these, I still have a functioning model. I still have some probability for every single possible value. Recall, we are working on the zero probability problem. We have basically solved the zero probability problem. But my estimate is now better because I know I rolled it, I sampled it, and I got 2. And so this one has a little bit higher probability than the other ones. All right. Now I could keep doing this though. And so I roll it again, and 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 I roll. Okay, I keep rolling. I keep doing this over and over and over. All right. Now, after a whole bunch of samples, I have the following, distribution. I can compute my probabilities. And you can see that things have gone, it was actually a strangely biased die, as far as we can tell. And my original estimates, my original prior probabilities are, as I do this more and more, they're getting washed away. These initial 6 pseudo counts, these pseudo rolls, if I do this enough, they will become a tiny infinitesimal portion of my estimate. And so my prior belief, which was uniform, will be replaced by something, an estimate, that's very close to the actual truth. But throughout the entire process, as I do more and more rolls, I've always had a model that has some probability for every single item in the vocabulary, the 6 values here. All right. So this expression, we can turn this into, make it look a little bit more like math. We can actually make it look like math, not a little bit more like math. And so we can say the probability of rolling some, this will be 1, 2, 3, 4, 5, 6 for I, probably the die. And what we'll say, this is going to be equal to the number of times we get roll of I plus the 1 pseudo count, as we started with that initial count in our model of uniform prior probability, plus, divided by the total number of rolls I've did, plus the 6 pseudo counts I started with. All right. And so this is a nice little formula for estimating this. Now you're like, that's all well and good, Mark. Now, can you bring it back to the world of information retrieval? You betcha. All right, so what about documents? So that's your question, or my question, I suppose. Well, the way to think about this, and it's a little weird, but it is, just bear with me as we go through it. Think about your documents as samples from some true model actually, I'll use the word topic. Some true topic model. Okay. What do I mean by this? Kind of the way to think about it is that the person who wrote the document, all right, so they had in their mind some sort of what we might call a topic model. And in fact, they didn't have a topic model. They had the thing that they wanted to communicate, and they wrote it out. But you could think about it if we were to envision it as they had a model. They asked the model, what's the next word, and 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 so forth, and they write it out. And they could, and then they decided to stop at some point. They could have kept writing is the idea. What's the next word, and 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 so forth, and so on, and so on, and so forth. And if you wanted to, you could pretend that, yes, their model was this big die. And they're like, let's roll the die. Hey, it said the word the. All right, let's roll the die. And it said the word shark. And then I rolled the die, and it said the word bit. And I rolled the word die again, and it said the word Bob. Oh, the shark bit Bob. Oh my, isn't that amazing? Now, it's very unlikely that that would actually happen because our model is so crude. But the idea here is that these documents are some sample of something that's producing words. And again, we're going to model the documents as these multinomials. So it's like, again, we've got these words that have been sampled from some model, and we're going to pretend the model is a multinomial. All right. And so just like the die, before the person writes the document, before we see the document, the best we can do is to have some sort of prior belief. Well, I don't know, what might they have written down? And one way to approach that is to say, you know, I think every word is equally likely, so let's go ahead and say my prior probability is uniform for all words in the English language, for all the words in my vocabulary, and that's what I'm going to start with. Oh, I see the document now. Well, I can update my prior beliefs now that we have this sample from whatever their model was. And of course, along the way, we have solved the zero probability problem, because when we start with some probability for every word, we'll maintain some probability for every word because we put a pseudo count into every little bin that is for every little word, just like we did for the die. and we will no longer have any zero probabilities. The longer the document is, the better our estimates will be. All right, so we do the same thing for documents then. Okay? And so if we do the same thing for documents, we do the same thing. So now we end up with probability of a word, given our model of our document, is going to be equal to the count of the word in the document plus the one pseudo count all over the number of words, the total length. So it's not unique words, it's the length of the document plus the size of the vocabulary. Okay. Yeah. Okay, so this is document length. This is the vocabulary size, total number of words. And again, think of these as all those little bins like we had for the bins for 1 through 6. So we had to have this number of bins for the number of each word. So that's the size of the vocabulary. And we put one count into every one of those bins, all right? And so now we'll go and we'll look at the document and say, how many times does this word appear? All right, and so that's the number of times that we saw it when we sampled it. We didn't, again, bear with me that this is the way we're thinking about it. And so this is a way to have estimates and build a model. This is no longer a maximum likelihood estimated model. This is now a smoothed language model, and we have eliminated all the zero probabilities. This happens to be called Laplace smoothing, named after Laplace. All right. There's a real downside to this, though. It's not the greatest smoothing approach. It's not really the best way for estimating things. One thing is, so issues, I'll start writing at the top, or I'll keep this on the board so you can see it though. Issues with Laplace smoothing, all right, is the size of the vocabulary is huge compared to the size of the document. So when I did the die, and we put one little count in each one, there's only a total of 6 vocabulary words for the die. And so before too many rolls, I've nicely sort of got a good estimate and swamped out the prior pseudo counts. With a vocabulary, our vocabulary is 1 million. And my document has 100 words in it. So sure, I've eliminated the zero probabilities, but boy, there are going to be a lot of words that have some probability that's not too much different from the actual probabilities I have for the words in my document. It seems a little strange. That doesn't go too well. Other issue, though, is you may have picked this up already, is that when I said, let's just assume every word is equally likely, that seems stupid. The uniform probability, I'll just say, I'll use that word here, is stupid given what we know about language. So we went over this earlier in the term. We know that there are words that appear more often than other words. We're not naive about language. We wouldn't actually think that we should give a prior probability that's uniform to every single word in the vocabulary. It doesn't make any sense at all. So, what else can we do? Well, instead of being uniform, Let's not be uniform in our prior probabilities. All right. So our first choice was uniform, and we just saw that that led us to Laplace smoothing. Then another idea would be, go back. So we're going to talk about the dies again. I know we're talking about words and documents. You're like, get me to the solution, but let's talk about dies. So I tell you this is a die in my hand, and I want you to estimate its probabilities. And, the uniform probabilities is not that bad for die. And the reason you feel it's okay is actually because you've gone through your life and you've grabbed a die and you rolled it and it's been a fair die. You go and you grab another die and it's a fair die. Basically, you can think about it as you've gone through life and there's these whole set of dies that you have interacted with in all these games and stuff in your life that you've played with. And you've sampled and you've used them, and it's another fair die. It's another fair die. It's another fair die. Now, you might at some point stumble across some friend's house and they have some trick die, some bias dies, and you roll them and it's like, whoa, what's going on? Like, this is so weird, what? And the friend goes, oh yeah, those are my trick die, please, I hope they call them trick die and don't say, oh, is that what I use when I go to Vegas? Because that's illegal. Don't do those sorts of things, okay? Let's say that they're a magician and they do it as part of an act or something, okay? All for entertainment and fun. And so you realize there's some probability of some of these things out there. So the way to think about it is you can think about your dies as you kind of like, you could draw, instead of thinking uniform probabilities, you could draw a whole die from this is the classic math notion with probability, from some urn. Actually, it's like we got this symbol, this imaginary urn that's filled with dies. All the dies in there represent the possible different ways and the proportions that those dies are. So in the real world, that urn, this imaginary urn, would be filled with a huge number of uniform dies. Fair dies, they're not biased, but there would be some biased dies thrown in that represent the probability of coming across them in life, So you could be drawing the dies, and of course different biased dies would be different from each other, but you could draw dies from the urn to see what the distribution of dies is like. Okay? And so you're not sampling an individual die and rolling one individual die. You're sampling from the space of dies. It's like, what are the possible dies that I could get? Are they tend to be like this or they tend to be like that? I find it a little mind-blowing to think about, we're not sampling individual rolls anymore. Now it's like we're sampling this whole big system, this whole big universe of models. We've got all these multinomials, and we're going to pull another multinomial out of it and go, what does that multinomial look like? And then we're going to pull another multinomial out of it and go, what does that look like? What are these probabilities for this multinomial? And I get a feeling for the distribution of multinomials, not the distribution of the outcomes of a multinomial, but what's the distribution of multinomials that I care about? And those I can then use to have an understanding about what the actual prior probabilities are for dies. Now, it turns out that there is a thing, of course turns out, that a Dirichlet density is effectively what would be a urn of multinomial dies. All right. Now you go, great, what's the Dirichlet density? We're going to leave it at, think about a Dirichlet density, okay, some distribution. It's going to be like, we're going to just think and know that all Dirichlet distributions are like an urn of multinomial dies. So if I had one of these things, I could use it to find out the behavior and the prior probabilities that I should assign to a generic model of a die. All right. Now, where could we find, let's go now back to information retrieval. Where could we find, if we're modeling documents as multinomials, that's like the die, and, you know, we want to understand about the nature of sort of a generic die, which again, how is the vocabulary used? How is the language used? Where could I find them? Where could I find such a collection of documents? Oh, a collection of documents, but of course, yay! All right, so we've got a collection that's sitting there. It's right in front of us. All of these documents, each one is a representation of the way language is used. We can use the documents themselves to tell us what words are most likely to happen and which ones are least likely to happen. Absolutely wonderful. So let's start and let's talk about a collection model. So we've got our collection of documents, and what we can do is we'll say the probability of the word given C, where C is our collection, is equal to the count of W, the occurrences, so in the collection C of docs, all right, divided by the total word occurrences in the collection C. All right, which is just going to be equal to C of W divided by the length of C. Okay, and this is basically what we're going to say is where C is all the documents concatenated together. So we're kind of skipping ahead away from our beautiful model of this urn of dies, but we're just going to go and we're going to straight up take the collection, and we're going to take it, all those documents, and it's just like we've concatenated and made one gigantic document. So, you know, it's as though someone was writing about shark attacks, and then they talked about crocheting, and then they talked about peace in the Middle East. It's just all one gigantic document. And then we apply maximum likelihood estimation over this one document. So what's the count of a word in that gigantic collection document divided by the length of the collection? All right. So what does this do us? Well, now we have a model that's this thing of how to distribute pseudo counts. So it's saying we have, oh, this is how the probability of words is distributed in the language across this vocabulary. This word is really common, this word's really rare. So this tells us what the shape of our pseudo counts should look like. All right. And then we have a separate question, which we skipped over with Laplace smoothing, which was how many pseudo counts should we have? All right. And our answer to this is going to be a thing called the M parameter. And so let me show you where the M parameter shows up. It shows up in the M estimate. So now we'll do a new model of a document. Again, we'll take the count of the words in the document, but we'll have M pseudo counts multiplied by the probability of the word given the collection, and we'll divide it by the length of the document and the number of pseudo counts. So this is the pseudo counts. This is also known as the equivalent sample size. All right. And so it's like, wow, Mark, that looks a lot like the previous formula. Absolutely. So we've replaced the size of the vocabulary here with how many pseudo counts we want to use. So now we've parameterized it and we have control. We've gained control over how much prior counts, how much prior probability we want to start with as we're aiming to get rid of our zero probabilities. And then we can say, well, that's how much I want. And then how should I distribute it? Oh, we'll use this model to tell us how to distribute it, the collection model. All right. So this overall, this thing, and if you do machine learning, you may very well see it called the M estimate. Okay. It's also known in the whole information retrieval literature as Dirichlet-Prior smoothing. And it does have, we can show math and stuff that shows that this is an example of treating all the documents, the collection, like it's a big urn of dies, big urn of multinomials, all right? And then we can end up with this as a simplified conception of that. And there are more complicated ways to work with this and stuff, but this is nice. Yeah, so the way to say that is that basically that can be shown that this smoothing technique results from having a Dirichlet density as a prior. So what is our belief in the probabilities before we know any data for a multinomial? All right. By That's pretty nice. I like that a lot. Now, so this Dirichlet-Prior smoothing works wonders. It'll get rid of all of our zero probabilities. So now every document in our collection has some probability, assuming again we give some. If we don't, as long as we don't set this to 0, okay. As long as we say there's some pseudo counts, every document will have some probability of having every single word in it, which is a little weird, but it solves the zero probability problem. Then, what else do I want to say here? I think one of the things I wanted to mention, it occurred to me before as I was going on, is why is it smoothing? So you think back to this idea that I had where we had the bins and we're putting in the counts and we get these distributions. Well, again, we form those from sampling the item. Okay, we roll the die. And when we don't roll the die very much, our estimates are probably not very good because we haven't had very many samples yet. And we can think about smoothing as kind of spreading out and making whatever that distribution be less jagged. So in other words, we got, oh, it's up here and then it's down here and we know it should kind of be, no, let's spread out those counts across everything and end up with a nice smooth distribution. That's the way I think about the word smoothing coming from. Anyways, so we've got this collection model now though, and we've got this Dirichlet-Prior smoothing, which is really great. But we might say to ourselves, like, oh, come on. Let's just handy dandy use this model in hand. Why go to this trouble with these pseudo counts and things like that? Let's just let's mix in the collection model with a maximum likelihood estimated document model. And how would that work? All right, so there's this other idea for smoothing. We have our collection model. Why not just mix it in? So this would be to take the probability of the word with the model of our document is going to be 1 minus a lambda. This is going to be a smoothing parameter. Probability of the word given the document plus our lambda of a probability of the word given the collection. And so this is a maximum likelihood estimated model of the document, and this is a maximum likelihood estimated. I should use either all caps or all lowercase. So this is a maximum likelihood estimated model, and so is this one. And what we're doing is we're mixing these two. We're doing a linear combination where lambda controls the amount of smoothing. Lambda varies between 0 and 1. And this methodology will show up, you'll see it with multiple names. If you're more in the machine learning world, you'll see in some other fields them just simply calling this linear interpolated smoothing, which is really actually a quite accurate name for it. And then you'll see in the information retrieval literature, this being called Jelinek-Mercer smoothing. And it's hard to find the original documents, but there are original documents where these people did linear interpolated smoothing, and then someone later came along and said, let's give it the name to them. It's like, all right. So maybe if you write something, someone later will name it after you. Okay, you come up with a method and they'll name it to be your method. Anyway, so we've got this linear interpolated smoothing. It doesn't work badly either. Okay, and it can work quite well. But one of the things that's often not known, unfortunately, is that it can be shown that Dirichlet-Prior smoothing is a form of linear interpolated smoothing. So it can be shown that good old Dirichlet-Prior smoothing is a form of linear interpolated smoothing. And you can do the derivation, but this is how you could see it if you plug things in. You go, if you set lambda equal to 1 minus document length over the document length plus the m parameter from the Dirichlet-Prior smoothing, this lets you, so you can take I've erased it now, but you can take the linear interpolated smoothing, and if you set the lambda parameter in it to this, you will do exactly the same smoothing that you do with the Dirichlet-Prior smoothing. It's exactly the same math. And so it's fascinating. So when we investigate and understand and look at smoothing, and we look at Jelinek-Mercer smoothing versus Dirichlet-Prior smoothing, it's important to remember, by the way, they are exactly the same method, just with different lambda settings. So they're both doing a linear interpolation of a maximum likelihood estimated model for the document and a maximum likelihood estimated model for the collection. And it's lambda that controls how much they are mixed together, but it is Dirichlet-Prior is set this way, whereas Jelinek-Mercer is just simply its lambda. Okay. Now, what's interesting about that is when you use Jelinek-Mercer smoothing, it means you smooth the amount of smoothing, the lambda, is the same for every single document, because all you do is set a lambda. When you use Dirichlet-Prior smoothing, this is for every single individual document. Every single individual document gets its own lambda. So documents get smoothed different amounts when you use Dirichlet-Prior smoothing. They all get the same amount of smoothing when you do Jelinek-Mercer, okay? In the form where you've only set the lambda once. So what does this mean? Well, thus it means that Dirichlet-Prior smooths shorter documents more. Basically, it trusts the counts less than long documents. And that is so very, very sensible if we think about documents as samples again. So a longer document is a better sample of this model that was used to write it. And so the larger the sample size, the more we believe it. Is what Dirichlet-Prior smoothing is saying. So if you give me a really short document, or let's say we're doing back to the die, you only roll it a few times. Ooh, you only roll it a few times. Whatever I've set for my pseudo counts will have a much bigger impact, and so I'll end up with more smoothing. Whereas if I roll a huge number of times, it's like the document length, I will swamp, this will be much bigger than my pseudo counts, and I'll swamp out the pseudo counts, and I'll effectively do very little smoothing, and I'll just trust my estimate from all of my samples. And so Dirichlet prior smoothing is really neat in the way that it's basically saying, you know, shorter documents get smoothed more because I don't have as good of a sample of them, so I need to rely more on my prior belief. But as the document gets longer and longer and longer, I have a much better estimate of how those words really are used in that document. And so I don't need my prior belief. I get to replace my prior belief by what I actually see. And so that is a really nice aspect of Dirichlet prior smoothing. All right, so that is largely smoothing, largely the language modeling approach to IR. Now, one thing I did not write down for you, though, was, wait a minute, when we did retrieval, and we did query likelihood, and then I said, oh yeah, and we could also have a more complex model of the query, and we could compare models with the document model. What is actually the formula? So you could find it in a book, but I want to put it here now. So we can do, again, language modeling. This is ranking by similarity of models. And I can just show you cross entropy. And again, it's basically produces the same ranking as we would get with the scale divergence. You can do both. You can compare them, whatever you want. But you'd have some model of a query. And that model that you have of the query could be your simple maximum likelihood estimated model. And if that is the case, again, remember, what I'm going to show you is going to be equivalent, rank equivalent to just doing query likelihood. So we could come up with something that's fancier than just a maximum likelihood estimated model of a query. You know, maybe we could even just say, you know, what I want to do is, you know, I want to compute some sort of complex model, and I want to find all the documents that are most similar to it. And then we could plug that sort of thing in here. And so we would need to be using this sort of a ranking methodology that lets us compare the models rather than talking about counts, because I don't really have counts. I don't really have the number of times a word appears. I just have a model. If I just have a model, I want to use some math like this. So this is the negative of the sum of the words in the vocabulary and the probability of the word given the model of the query multiplied by the log of the probability of the word given the model of the document. So this is cross entropy with the stipulation that when we get a 0 log 0, we set that to 0, and that if we have a probability of the word given the model of the query that is greater than 0, but, well, I'll say and here, but the probability of the word given the model of the document is 0, then we say the score is minus negative infinity. Okay. Because again, so what's the cute thing that we do here? If it's not in the query, all right, so probability 0 here will make this thing be 0. But if it was a query term, okay, and my model has a 0, then it's going to be negative infinity. It's basically at the bottom of the ranked list. And you're like, wait a minute, that sounds awful. But don't forget, our models of our documents will be smooth models of documents, okay? So models of the documents will always have a non-zero probability because we solved that problem. So that's not really an issue. What it really ends up being then is we end up with this ranking methodology now where we've got some weight for the term in the query, multiplied by a weight for the term in the document. Ah, doesn't that look really, really, really familiar to you? Absolutely. All right. Effectively, what we end up with here, these probabilities for the document, after we do the smoothing, and remember we do our smoothing, we like to pull in this collection model, okay? Effectively, we can show in the math, move it around, and before you know it, you can see that we've put in an IDF into the weighting via the smoothing because of the collection model. And so this weighting here of the document ends up having a mixture of both the term frequency, that's sort of the probability that's in the document, and then when we smoothed it with the collection, we ended up producing an effect that's an IDF effect. And so again, we have a TF IDF here, and then this is just weighting them all by the importance of the words in the query, which is basically the count of it. So this is super similar at the end of the day. It's a much more complex thing to understand than the direct models for the cosine or the BM25, but it has a lot of the similar ideas in it. And the language modeling approach, once we have smoothing, is a very effective retrieval methodology, but it's never been found really to be significantly superior to BM25 approaches. And the BM25 approaches are a bit easier and sort of directly we can see what we're manipulating, and there's something very appealing about that. But what's nice then about what we see here with the language modeling is it's kind of like, so we can kind of feel like we're going from first principles of I want to have a model with probabilities and I want to compute these things and I want to come up with a good estimate for a document, an estimate for a query, and I can measure these things, and these are nice mathematical properties, cross entropy, how it gives us a measure of how well we are representing these models with one with the other. And we end up with good retrieval quality. Yeah, but when we do tear this open, we find our term frequency in IDF and our document length normalization all being very important. So these sort of key components that are in the BM25, it's only because they also show up here that this works. And you might say, well, which one comes first? Well, this might point to there's something natural in language that if we do it this way, we end up with good retrieval. And it's just that BM25 figured that out. But BM25 actually came from, I didn't show the derivation, but it comes from doing a model of trying to classify documents, all right, as either relevant or not relevant. And so all of these approaches really are coming from the same sort of idea that I have these two classes, relevant documents, not relevant documents, and I need some way through counting of the terms and things to really figure out how to pull those two classes apart and rank the things that should be found, that we hope will be found relevant by the user near the top, and push the other things down to the bottom. All right. I'm not going to talk any more about these sort of similarities, but they are all interconnected, but fundamental ideas stay the same. So this is ranking with models. We've just done smoothing. This does not work unless, and language modeling approach doesn't work without the smoothing. And in general, if you're looking for a good general purpose smoothing, it's Dirichlet-Prior smoothing. All right, very good.